Exercise axial load. This problem, we read the problem before. The two faces of the clamp. Firstly, we set the distance between the two faces to be 250. And then is connected together by the two stainless steel. This one stainless steel. And then we apply force P. We apply force P, any force P, to deform the steel, steel rod, to deform the steel rod. And we apply P until the steel rod extend more than 1 millimeters. And then we push, we place the aluminum alloy bar, this one, in the middle. The aluminum alloy bar, the length, the initial length is 251. And after that, we release the load. This one, we release the load. So the two faces want to return to the initial position, that is 250. But there is the aluminum bar with length 251. So it cannot return to the initial position, but it will return to some location. And the force should be induced in both aluminum bar and the steel rod. And we want to find the stress in bolt and in aluminum bar. And always we want to find the change in length of the aluminum bar at final position. And so for this one, we should start from draw the free body diagrams. And so we draw free body diagrams by cut here. So we draw free body diagrams at final position. We must know that at final position, we must know that the force P is removed already. So there is no external load. So at final position, the equilibrium at final position. So the force, there is only the force in steel and in aluminum bar. And by considering the system, you can see that you put the members, and then you release the load. So the load, the two faces will push the aluminum bar. So in aluminum bar, the force should be tension or compression. It should be a compression. Place the aluminum bar. And so to form equilibrium. So the force in steel should be in opposite direction. So this is the free body diagrams at final position. No external load, and there is only force in both members. And form equilibrium. So sigma f x is 0. So 2 Fst minus F aluminum is 0. So we can find 2 Fst is equal to F aluminum. That is one equation, two unknowns. So we can solve this by using only equilibrium. So this one is the SI problem. SI problem. This is one equation, two unknowns. So this is SI problem. So we have to find a compatibility equation. By comparing the initial and final and the constraint. For this one, the constraint is the difference between two members. So we for this one we draw the reference. This one reference fixed, maybe we consider this phase when we consider the compatibility this fixed phase. So the rod, steel rod, the length of steel rod, this is steel. The initial length for the steel rod, the length is, for this one, the length is 250 millimeters. How about the aluminum bar? So for bar, a bar, aluminum bar, the initial length for aluminum bar is 251. 51. And when you release the load, so the load, the phase, at the right, want to return to the initial position or want to return to this position. But when the phase touch the aluminum bar, it cannot move freely to the initial position here. It cannot move freely. So it will stop at one location between this line and this line. So between this, this is 1 millimeters. So final position for the phase at right, it should return to somewhere here. So this shows the final position of the phase of this phase. So this is final for that phase. So it should be final for aluminum bar and final for steel, steel rod. So you know initial of steel. This one initial of steel. Initial steel. And you know final of steel. So this distance is del steel, or the elongation of steel. And from the aluminum bar, so this location is initial of aluminum. And final is here. So this distance is del aluminum, the compression and the contraction in aluminum. From the picture, can you find the compatibilities? So the compatibility is, from the picture, you can find the compatibilities. That is del steel plus del aluminum. So it should be the elongation in steel. From the force direction, it should be the deformation if you put F steel. Put force in steel by F steel, and plus the contraction in aluminum. So if you push compressive force in this equation, so it's you can calculate magnitude, and this value at meters is equal to 1 millimeters. Let's change to basic unit. And then we will calculate this. Del steel, the elongation in steel, so we put the tension force in steel, L steel divided by E steel, A steel. And plus del aluminum, it should be the contraction in aluminum. So we add compressive force, L aluminum divided by E aluminum, A aluminum. Is equal to 0.001 meters. Input the values. So the values is F steel. The length of the steel, consider the picture. And the length of the steel should be this one plus this one and plus this one. The length that can change should be these three values add together. And so the length of the steel is 0.33 meters. divided by the E steel is for this problem is 190 gigapascal. Change to basic unit. Okay, and the area is steel. The bowl cluster area is 120 millimeters square. Okay, so this one multiplied by this, okay, meter square. And plus F aluminum. L aluminum is the initial length 251 millimeters divided by G aluminum is 75 pascal. Okay, and area is 625 10 minus 6 meters square. And so this one is equal to 0.001 meters. So from this equation, you can find more one equation. That is equation number 2. So from number 1 and number 2, so you can find F steel to be 39252 Newton, and F aluminum is 78504 Newton. But this problem, we want to find the stress, so we will calculate the stress and the deformation. So this is the value from calculation, but this problem, I want to find the stress, so the stress can be calculated from F over A, and so the stress in steel is S steel over A steel, and so 3922 Newton divided by from the problem, and the area is 120 millimeters square, and so you can find the stress megapascal. Newton per millimeter square is megapascal, and sigma aluminum is F aluminum divided by A aluminum. So this one is 78504 Newton divided by from the problem 6 millimeter square. So the stress is 125.61 megapascal. And we want to find the change in length of aluminum. So we want to find the aluminum. So we apply FL over EA. So it should be the contractions. So del aluminum is F aluminum is 78504 Newton. The length is the initial length 0.251 meters. The E is 75 multiplied by 10 to the power of 9 pascal, basic unit. And the area is 625 minus 6 meters square. And so from this calculation, we can find the deformation in meters. This is in meters. And so we can find everything. To show the answer, a student must define the direction or the meaning, the physical meaning of each value. And so in answer, when you show sigma in steel, the stress in steel is 327 megapascal. Now you choose show the direction, because we know that the force in steel is a tensile force, and so the stress is a tensile stress, and so we define tensile. The direction, and sigma aluminum, the magnitude is 126 megapascal, and the direction is in compression. And the aluminum, the value is we use millimeters, 0.432 millimeters, and we show it should be the contraction. So show the physical meaning of each value in answer.